Yesterday we were working on greatest integer function, right? So we got through a little bit, but not a lot. We're right here looking at how these negatives affect the graph. So, sorry, just a minute. There we go. Okay, so we graphed the first one, right? But then we weren't sure what we were going to call it. That's where we left off. Okay, so we were looking at the graph of the first one. Where did my special pen go? So look at it right now with your group and decide if you came up with, based on where we left off yesterday, what would we say happened to get from the parent function to this graph that we have of f of x equals negative greatest integer function of x. Okay? So what change was made? How do we transform it? Have your group make a decision right now, and then I'm going to ask you guys. All right, so the green one's the parent function. The red one is what you have on your graph for this function. So any group think they've come to a good decision of how to describe what has happened as a transformation? Emma? Good. So this is a reflection over the x-axis. Okay, so we're going to write that down because it's going to be important for us to understand that when we see this negative, we want to reflect over the x-axis. Is everybody okay with that visually here? So the green one is the parent function. Notice this step is the same because if I'm on the x-axis and you're reflecting over the x-axis, I'm still on the x-axis. Look at this green step from the parent function. It was right here. It was 1 unit above the x-axis. So when you reflect it over the x-axis, it would now be 1 unit below. Okay? This step gets reflected here and here. These ones below the x-axis are getting reflected up there. Okay? So it's definitely a reflection over the x-axis. Another way that we can understand that is look at where the negative is here. When we made the chart for this, we rounded first, and then when the rounding was done, we applied the negative. So I want you to think of like, if you had a chart for just the parent function, and you don't have to write this down just so that you can understand. In the parent function's chart, the x's were the numbers before they were rounded, right? And then the y's were those values after the rounding was done. Is that okay with everybody? So like, we can think of the input as before the greatest integer function was applied, and then the y values are after the function was applied. Is this negative something you would do to an x value before you ever did the rounding? Or is this position of the negative something that we would do to the value that we got after we were done rounding? After. That's what we did when we plugged stuff in. We rounded first, then we applied the negative, right? So it's like that negative ended up being applied to the y values because they were the values from the parent that we got after we rounded. And then it makes sense that it would flip over the x-axis because if you had a point previously, like 2, 2, and you applied a negative only to the y value of that point would then be transformed to negative 2, which is a point that we would now see in our reflection. So by changing the y's, by multiplying the y values by a negative, every y value that was above the x-axis now becomes a point that is below, and every point previously that was below the x-axis When its y coordinate now gets multiplied by the negative, the y turns positive, and so now you see it above. Okay? So we're changing the y coordinate, but it's flipping it over the x-axis. Is that okay with everybody? Okay, so a negative out here is going to be a reflection over the x-axis. So what do you think is going to happen then if we apply the negative before we round it? Okay, so if we thought about our parent function, if there's a negative in here with x, are you applying the negative to those before they were rounded values or the after their rounded values? Before. If you take the parent function chart that existed and you take every x from that chart and you put a negative with it, you're going to take every point that used to have a positive x is now going to have a negative x. So I'm going to do this one a little different. I'm going to put the parent function right up here. You guys don't have to draw the parent if you don't want to for your notes, because if you want just one example of what this function actually looks like, or you could do it really light in the background. And then I'm going to go through this and think about what this change would do if I'm taking all the x coordinates and multiplying them by a negative, right? So I'm going to start right here at 0, 0. That would still stay, still green, at 0, 0. Okay? But then all these points over here, let's think about one in particular, 0.5, 0. If you now apply a negative to the x, what does that point become? It was 0.5, 0. So now it will become negative 0.5, 0. So this point that was right here is now over here. Okay. What about this open point? It was at positive 1, 0. Where will it be now? Negative 1, 0. If I'm changing the sign of the x's in each point. So this step is now being transformed like this. Okay? Let's look at another step. Okay? This step right here, this first point, the filled in one is 1, 1. Where will the new location be if we're changing the sign of the x coordinate? Negative 1, 1. So there it is. Okay? One of the points on this step was 1.5, 1. Where will I now plot that point? Negative 1.5, 1. The other end point of that step was at 2, 1 with an open circle. Now that point would be plotted at negative 2, 1. What is happening here by applying the negative to the x's from that parent function instead of the y's? What is happening? What kind of transformation? Right? Yeah, now it's reflecting over the y-axis. Each of these, they were on the positive side of x. Now they're moving over to the negative side of x. And that's causing them to flip over the y-axis. Now you might think these look the same, but they actually have some big discrepancies. They both kind of have this trend that they appear to be kind of like downward sloping than upward sloping, if you want to refer to that. However, notice how the endpoints have changed in this one here. Okay? The endpoints didn't do that change over here, and it had to do with how we were reflecting it. When we were reflecting it over the x-axis, you still went from like solid to open endpoint. However, when you flipped it horizontally, you not only changed the orientation of like the staircase in general, but each step's orientation was kind of flipped over. Okay? So this negative in here is causing a reflection over the y-axis. It's the x that is changing, but when x's change, they change from side to side over the y-axis. Okay? Is this okay with everybody? So when we see negatives, we have to think reflections, and then we kind of have to sort out which one based on where the negative is being applied to. And you could either straight up memorize which one is which, or like we talked about here, I see this as a negative being applied to y values. When I switch y values, I'm flipping over the x-axis. I see this as a negative being applied to the x values. when you change the signs of x values, you're flipping over the y-axis. So whichever way kind of helps you differentiate which one is which. Okay? Any questions about our reflections? Okay, so now let's see what happens when we put some like number values in there. We know how the negative will affect the graph, and now we have to figure out how the number values will affect. And again, we're going to start with plugging in to kind of learn how it's working, but we don't want to have to plug in later, because later you're going to have things that have negatives and numbers in every spot, and it could get really complicated to plug in. Not to do the calculation, but to make sure you're actually getting endpoints and stuff like that. You might not know where they are. So we want to generalize it and make it a little faster for us later. But again, to learn it, we're going to start. So I'm going to start still with -1, 0, and 1. And look at what we're doing here. We're multiplying by 2. Okay? But in the next problem, we're also multiplying by 2, just in different places. So in this one that we're not to yet, the 2 will be multiplied before we do the rounding. But in the problem we're working on, we're going to round first and then multiply by 2. Is that okay with everybody? So I plug in -1, it stays -1, I times it by 2, and I get -2. I do this with 0. 2 times 0 will give me 0. And I do this with +1. 2 times +1 will give me 2. Okay? I'm going to go ahead and plot these points to start with. So I have the 1, 2, 0, 0, and -1, -2. This looks a little different than we're used to, right? How is this different from the parent functions or when we were just applying a reflection? How are the points I plotted a little different from the parent? Right? Good. Okay, what we normally think of as the slope looks different for these points than it did for the parent function. So then the question is, like, is it really different? Am I missing something in between that I'm just not aware of yet? So I'm going to try plugging stuff in and see what happens in between. So let's go ahead and do 0.5. Kind of in between 0 and 1. So when we plug 0.5 into the greatest integer function, what does it get rounded to? 0, because we can't go past the value that we have. So 0. And then 0 times 2 would be 0. So 0.5 times 0. Okay. And then let's say I plugged in, I'm like a little odded out by the fact they're like more spread out than they were before. So I'm just trying to check a couple, make sure we didn't miss anything. So 0.2, if we plug that into the greatest integer function, it gets rounded to 0. And 0 times 2 is 0. Okay. What about like 0.9? Still 0, right? Because it still gets rounded to 0, and 0 times 2 is still 0. Is there any number between 0 and 1 that would work out differently than this? No, because all of them would be rounded to 0, and then times 2 would still be 0. So this step is still like it was in the parent function until we get to 1. But then the difference is when we plugged in 1, it doesn't go up to 1, it goes all the way up to 2. Okay? So once I've determined the length of my step, and that this endpoint matches with that one, I didn't miss one in between, I basically have the rest of my graph, right? The steps are 1 unit long, and how far apart are they? 2. And there's no negative, so they're not like reflected any weird way. They just follow the normal stepping pattern. So now I just know to keep drawing the steps 1 unit long and 2 units apart vertically. So how would you summarize what a numerical value in this like A spot, if we think of like the A, H, and K from absolute value setup, what does putting that numerical value in that A spot do to our graph? Okay, so it changes the slope, which we can't technically call the slope anymore because slope is like rise and run of the connected lines. And the problem is the slope's almost been split into 2 parts when we do the steps, because there's a distinct vertical part and a totally separate horizontal part, because instead of connecting the dots, the steps like have their own life to them, right? And then they like jump to another one. So you're right, but we have to change the wording of slope. What specific part is it controlling? Eli? Good. So the y distance, the vertical distance between the steps seems to be controlled by this number right here. And we could see that if we change that number to a 3, these would be 3's because we'd be multiplying by 3. And so it's a really nice relationship. That basically is the vertical distance between the steps. So that's really nice. Oh, sorry, it got connected between steps. Okay, so vertical distance between steps. So now when we see a number there, are we going to go plug in all this stuff? No. We are going to start our function where it starts like normal, and then according to that number, just adjust how far apart our steps are. We don't have to do this crazy plugging in stuff over and over again every time. Okay? All right, so now let's see if it's the same or different if the 2 is in here. With absolute value, it was really, really nice because we talked yesterday how we could just separate the number and we could always put it in the AHK form. We can't do that anymore with this. Like, how do I take this 2 out? Like, I don't know what it was multiplied by to round it. Rounding is different than just changing the sign of a number. So that 2 doesn't get out of these brackets. It's always going to be in there because I don't want to make any assumptions about how it would be rounded. So I can't change it, so I better learn how it works. So what happens when we put the 2 inside of the greatest integer function, which means we multiply by 2 before we do the rounding. Okay? So -1 multiplied by 2 would become -2, and then it would stay -2, so we're going to round it to. 0 times 2 would be 0, and 1 times 2 would be 2. Okay, so I'm going to go ahead and plot those 3 points to start, which don't look any different than what we started with over here. And then I'm going to go plug some stuff in between, just like I did before, because I'm uncertain about how this works and we want to figure it out. So let's start again with half, okay, kind of halfway between 0 and 1 to see what's happening in there. When I do 2 times half, what do I get? 1. So this is distinctly different than what happened over here. Over here, everything between 0 and the 1 was the same because all these numbers got rounded back to 0, so it was like I was using 0 over and over and over again. However, now that I'm multiplying by 2 before I round, I just took an x value that was a fraction, but because I multiplied by something before we rounded it, I turned it into a whole number that I didn't get yet as a y value. Does that make sense? So half times 2 became 1. That doesn't need to be rounded. That is now 1. That means there's a whole nother jump in between here now, right? That's jumping to a new whole number. So at a half, I need my eraser because my things are too thick. But it's as thin as it will be. Okay. So at a half, we're jumping up to 1. I know. It's like a little bit poorly calibrated. Oh, no. Okay. We'll just do that. Okay. Yours was probably a lot quicker than mine was. All right. And then to kind of just confirm this is actually happening, I'm going to go over here and see what's happening at that half value between 0 and -1. So at negative half times 2 would make -1. So again, there is another step in there as well. So this wasn't what I maybe expected, but there's something going on in there. And now I'm going to look in between those just to make sure I didn't miss anything else. So like in between 0 and 0.5, let's say I do 0.2. So 0.2 times 2 is 0.4, and that would be rounded to 0. 0.4 would get rounded to 0. Okay. What about like 0.1? Is there anything else between 0 and a half that when you multiply it by 2, it'll make a whole number? No. So these will keep making decimal numbers, and they're going to keep getting rounded to 0 until that half where it jumped up to 1. So all x's are going to keep getting rounded to 0 except for there at a half where it jumped up to 1. Okay. And what if I plug in something like 0.7 past a half? 0.7 times 2 would be 1.4. How does 1.4 get rounded with this function? To 1, right? Okay. So anything in here is going to make a 1 point something when it's multiplied by 2 and get rounded to 1 until we get to that next jump. So this is going like this, and it gets up here. So if I follow this pattern, sorry for my drawing. These are hard to draw. They're little. Okay. I have something like this. How is this different from our parent function? Elin? Yeah, the distance between the x values got closer together. So I would venture to say that this number here is controlling the horizontal length of the step. That's what it's affecting, right? So it controls the horizontal length of the step. However, there is something mysterious happening here. It said 2, but how long are my steps? Half a unit, Emma.
So that would be like there's double the amount of points per like the paragraph.
Yes. Okay, so like the x's are getting to the y values 2 times faster than they were before, which means it used to take me all the way on the graph to 2 maybe to get up here, but now I'm doing that in half the amount of time because I'm going twice the speed. I'll show you guys another way as well. It essentially means that you had some chart before where to reach a y value of 2, you had to go through 0, 1, 2. So it took 2 units of x value to the value of 2. Now, with that 2 there, you're going twice as fast, so it actually only took unit in x. Because you're moving twice as fast, it's actually taking less time to get to that y value, which is making the step shorter horizontally, okay? So we see 2, but we don't actually make our step 2 units long. What is the relationship between the number you're seeing in the equation and the length of the step? So what if I change this to a 5? How long would my steps be? Yeah. Good, 1/5. What if I changed this to 1/4? How long would my steps be? 4. Okay, what's the relationship between the number in the equation and the length of the steps? What do we call that? 1/4 means 4. 2 means a half. Yeah. Good, the reciprocal, okay? So we might want to make a note for ourselves here to use the reciprocal. And again, I know it's a weird idea. The number here means you're speeding, so this means 2 times as fast, but that means it takes less time to do it. Okay, so smaller steps. When you put the 1/4 there, that means 1/4 as fast as you used to, which now means it's a lot slower and the step is going to take longer to get there. She was like, I have grades. All right, are we good with this? So these numbers now control different things because the slope has kind of been split up into 2 parts, right? There's a distinct vertical separation, but there's a separate length of step horizontally. So, and it kind of makes sense. This 2 was applied after we were done with the rounding. So that means the 2 is affecting the numbers from the parent function that you had after the rounding was done, which was like the y values. So that's why it's affecting something vertical. Where this 2 is being applied before you do the rounding. So in the parent function, that would have been like the x values were the numbers before they were rounded. Okay, but the relationship's a little bit weird, right? But we still understand that it's something horizontal because it's affecting the x values. Okay, is this all right with everybody? All right, so we're going to try and put it all together and use our parent function and this like deep-seated knowledge of how things change when these numbers come in to do the graphs at the bottom that have numbers in like each spot. Okay. Don't say, oh, it's going to be great. Okay. It's going to be so good. All right. So here's our 2 problems that we're going to graph. Stretch out, do whatever you have to do. All right. Okay, so first of all, remember the format from absolute value that was really nice, the A, H, K idea? So all of those things still apply here, except for this function was a little unique that a is not the complete slope because that doesn't account for horizontal length and then vertical separation. But we still like that format. The only problem here is every absolute value could have an A, a H, and a K, and we can't do that with here. Like, I can't get this 2 out of these brackets. Yes?
So, for the two numbers that we just did, first that's it's like rise.
The vertical,
First one is rise, and the second one is run.
But they have to be separated into 2 different places because we're not just connecting like dots. We have like full steps that take up the place before they're separated vertically. Okay? So our equation now, we just have to adjust a little. We're still going to have A. We're still going to have H and K. But then we have to like throw a B in there also. Because we can't, absolute value had that cool, like, I could factor everything out of it, right? Because all it did was change the signs, but we can't do that anymore. So we have to, like, we want to label that number, and we understand now that number serves its own purpose, horizontal control of how long the steps are, okay? But it's always going to be separate. The other important thing here that we're looking at is that the x minus h still needs to be like its own little group, even if this still exists inside of the function. Otherwise, you won't know what it shifted left or right. When you guys did your absolute value investigation, you had to have x, one x, plus or minus a number for that number to like match up with what was happening on the graph. You can't have a negative or some other number here affecting x if you want to see that shifting left or right. If you want to know what that number is, it has to be separated into its own little x minus h bubble so that we can see it in the exact format in which we studied it. Okay? So when I look at this equation here, I'm going to actually rewrite it. 3 is the A value. 2 is the B value, but I don't really know my H value yet. I see the minus 4. That is not necessarily my H value because I need to separate the B from the x minus h quantity if I want to see the true h value that corresponds with the graph. So this would become, when I factor out a 2, x minus 2. And notice when I say I factored out a 2, I factored it out of this quantity. I didn't take it out of the brackets. I don't know how to do that. I don't believe there is a way. Okay? But I now have it written in a way where I can actually see an A, a B, H, and K values. Right? And our H and K do the same thing that they did before. What do they do to our graph? What type of transformation do H and K control? Yeah. Good. They tell us the vertex. And in this case, there's not really a vertex, but there's still a starting point. We always started our steps at the origin. But now our graph has been shifted 2 to the right, because H is positive 2, even though it says x minus 2, right? And then 1 up. So given that H is 2 and K is 1, I'm going to have a new starting point for this step function at 2, 1. So 2, 1 is going to be my starting point rather than 0, 0 because of shifting, right? The whole graph is being shifted. The other thing that I always keep in my kind of head is that the step function generally looks like this. Steps that are 1 unit long and 1 unit apart and go like this. Unless there's a reflection. Then I honestly sketch this on my paper and then I like redraw it with the reflection real quick so I know which way I want my steps to go in my final answer. Is there any reflections in the current question that we're working on? No. Then even though I'm going to move them or stretch them apart or whatever, my steps should still look like this in the end. So this is the picture that I'm going for, okay? And I so far have one endpoint. So if I can just get from that endpoint how long to draw the step and then how far to jump to the next step, I'm golden, right? Then I just have to follow the pattern and get through the rest of the steps. So what up here is going to tell me how long to draw my step? I see Ewan. He's so on top of this part. He's got it down. Chris.
So it's going to be the run value, which is 2, but it's the opposite. So it's 1.
Good. Does everybody understand what he's looking at? This B value right here affects the horizontal length of our step, but it has that weird relationship where the 2 means it's getting there twice as fast, which actually means like the step only takes half as much space up as it used to, okay, because we finish it quicker. So our step is going to be half a unit long from this 2 right here. So that's the horizontal length. I'm going to draw my steps half a unit long. Okay? I'm going to go ahead and from my start point right here, not in any weird direction, no reflection, so I know I'm just following the like starting point. Over, up, over, up, over, up. Okay? So half a unit. There we go. All right. Now all I need to know is where to draw the starting point for the next step. I already know it's going to go up because I'm following the basic pattern of the steps, but the question is by which distance? 3. Do you guys know where he's picking 3 out from? Which value? The A value, because remember the A controls the vertical separation between our steps. So this tells me my steps are 3 units apart. So 3 above this, I'll draw my new step. And then I will just use that pattern to fill in the rest of the steps on the graph. Is that okay? It's a lot better than plugging in points. Look at that equation. It's not the multiplying and rounding that would bother me. It's like, how do I even know if I made it to the next end point or not, or if there's something in between that would get really complicated. Chris?
So we've done A for AH, A. We already got A and B. We're going to do C, D.
Nope. This is it. And if we understand what these do really well, we get to use these over and over again. So step functions, quadratics, every type of function, we can just take the parent and be like, oh, you're like pushed down this way, stretched out this way, flipped this way. And like we can apply the same idea to a different function throughout our entire course. So it works pretty well if we can grasp it well. Okay? All right, so let's look at 15. So 15 kind of looks like you don't have a B value, but it is slightly different than just having 1 because it has a negative. So we still need to rewrite this with the 1/2, and we need to factor the negative out. Because I said you need an x minus h group. It didn't say negative x minus h was the formula for h to be the left-right movement. Okay? So if you don't do that, you'll get your h value incorrect. All right? All right, starting point of this graph. Somebody new who feels like they've grasped this idea of where we're going to start this step function and can tell me where to put my first point. Alex. Close, but positive 3, 0. Is that okay? Yeah, because of the tricky x minus h. So we're going to put it here at positive 3, 0. All right. Is there a reflection? Yes. Okay, so I personally, you might be light years ahead of me. I'm not going to lie. Many of my students will easily surpass my level of knowledge. I get you guys are very gifted. I need to draw a little picture, okay? Because there's 2 different types of reflection. They make the steps go 2 different ways. I now know my picture is not going to look just like this, and I just want to know what the pattern is to follow, so I'm just going to sketch it for myself over here. What kind of reflection are we having here if the negative is here? Are we reflecting over the x-axis or over the y-axis? Y-axis. The x's are changing, but when we change x's, it flips over the y-axis, right? So, new picture. When I flip this over the y-axis, my steps look like this. Fair enough? So now from my starting point, I don't want to draw the step going to the right. I want to draw it going to the left and hitting the open point. And then I'll go up to whatever the next separation is and finish that. Is that okay with everybody? But without this picture, I don't want to follow the wrong pattern. So I don't really need to do anything for this except for picture in my head the way it's changed, like the setup of the graph. But for me, I don't picture it in my head. I draw it right here. Okay? All right. So now, in order to follow that pattern, I have my endpoint up here. I need to know how long to draw my step. So can somebody raise their hand and tell me how long my step is horizontally and how they knew? Hunter.
Isn't it just 1?
Yep, it's just 1. And he's saying just 1. Not like that's not as valuable as any other number, but it didn't really change from the parent function. There was a reflection, but there was no other value here changing that. Okay, so there's my step that's 1 unit long. Okay? Drawn in that direction because I visualized my reflection right here and I know how the graph is going to behave and look based on that reflection. Okay? All right, last thing I need to know, how far apart are my steps vertically so I can get to the next step? Feeling? Good, 0.5. So now I just have to go up 0.5 to start my new step and draw it, and then I will follow that pattern. So starting point, reflections will change the basic setup and structure of our steps. And then those A and B values and how they relate to how long the step is and how far apart each step is. Okay? Any questions about those before we try to go write domain and range? Alex? Good. All because of this A value. Okay, so what we established from the things we graphed before is this A value is kind of like the vertical element of our slope. It's just telling us how far apart our steps will be. So given that it was 1/2, they're a 1/2 unit apart. Okay? Yes. So the way I knew which direction to go was solely based on what it would look like when I'm finished. So if there's no reflections, I use the parent function. So the red that I had drawn up here was the parent function before. And I drew that to help me with this graph. This graph had no reflection, so I made sure the steps starting point next up to the right. Whenever there's a negative in the function, that's going to cause the whole setup to look a little different because of the way it gets reflected. The negative in here meant it's changing x, but to change x means you're flipping over y. So I took the parent function and I redrew it as if it had been flipped over y, and I now know that the steps in this graph should follow this pattern instead because of that negative causing that reflection. Okay? If the negative had been out here, I would have reflected this way, and then I would have followed that new pattern that I saw. So I have this like little mini sketch over here to tell me like, hey, this is what it looks like, and then when there's a negative to be like, don't draw it like that, draw it like this instead. Okay? Is that all right with everybody? Okay. And you can always plug in some points and check, but do you see how now like making the whole table might not be the most efficient way to graph because there's so many changes? You could miss some endpoints or something like that, and it would cause your graph to look probably a little silly. You wouldn't see the nice pattern of the steps. All right, so domain and range. Let's talk domain first in general. Domain for any greatest integer function. What is it? Keelan? All real numbers. Why is it all real numbers? Right? Yeah. There's nothing you can't use, right? This function rounds thing. Is there any real number that if you plug it in, it can't round it? No. If I plug in pi, what does the greatest integer function do to that? Turns it into 3. Okay? So there's not any number that you couldn't put in here and get an output. So all real numbers works for the domain for all of these functions. So domain is all real numbers, or if you like writing it in interval notation, negative infinity to infinity. And so I'm a little bit flexible on tests with writing domain and range. I don't care if you guys use inequalities or interval notation. But when it says like increasing interval, you have to use interval notation. So I'm going to ask you that anywhere it says interval, that you use interval notation. So I am making sure that you learn it because you're going to be asked that for like absolute value function and stuff like that. You're going to have to use it. But when you write domain and range, I'll let you use whatever method you prefer. Okay? Yes? With the parentheses or the square brackets from the minimum to the maximum value that it can be. Okay? Now, we don't do all those characteristics for this graph because, like, what's the vertex? Like, we had a starting point, but we didn't really have, like, a vertex. And, like, what's the increasing and decreasing interval? Like, none? Like, it goes flat the whole time? You're never on a piece that's actually climbing? Like, those are weird characteristics for a graph like this. They work a lot better for things that are continuous and all connected. So we usually only use them here. For these skills, skills 7 and 8 in this unit, we are asking you these two things: graph greatest integer functions and find domain and range. So that's what the expectation is. Okay? Question? Oh, you're going to give me the range. Tell me about the range. Well, okay, so the fancy Z meant integers. What's our issue now? Like, let's look at this graph. We've skipped some, right? Let me tell you what we have here for a minute, and then we'll talk about how to write it. We have this number, -5 is part of the range. But then the next number is 1 is part of the range. 4 is part of the range. It will go on. So it's basically an infinite list of these random values that our steps hit. There's a better way to write an infinite list in kind of an equation format, okay? Look at the list we've created. How far apart are each of the numbers? 3. So there's a pattern here, like a slope on a graph. Like you follow the pattern and you get to the next point on the line, right? So if we keep going increments of 3, we'll get to the next number in the answer. So for range, we're going to y equals, because range is y values. We're going to use a 3 something. Just brought in a new letter. It's K. I don't know why they use K. I think because it's not being used for anything else, and then it won't get confused with like X or anything like that. But the reason 3 is being multiplied by something is because we don't just want to use one slope. You want to use it over and over again, and people can use, like you could actually go 6 or 12, but any multiple of 3 will get you to these numbers, right? Okay. Unfortunately, these aren't exactly multiples of 3. Like 3 times 0 would be 0. That's not on this list. 3 times 1 would be 3. That's not on this list. So I need to adjust slightly. It is every 3, but it's every 3 starting at one of these numbers here. So kind of like a linear equation. Use your slope to say where for people to go, but you give them a y-intercept to start at, right? Like start at 2 and then use this slope over and over again. So we want them to use 3 over and over again, but we need to give them a starting point from this list. You can honestly pick any value you want. It doesn't matter. 1 is nice and simple, so maybe I'll pick that. So 3 is the pattern that you see, how far apart the numbers are. So make a little note if you have to do that. And 1 we just picked because it's one of these numbers. We could have picked 4, -2, -5. We could have picked 7 or -8 because those would also be on the list. Okay. And then we have to make one little note. People don't know what K is. We just threw it in there, right? We want K to be like jumps of 3. So like 3 times 1 or 3 times 2 or 3 times 3 or 3 times -1 or 3 times -2. All these numbers I'm saying that I would like to multiply by 3. Do I want to multiply 3 by like 1.4? No. I want them to use exactly 3 each time they go, right? So no decimals, but they can use positives or negatives or 0. What kind of numbers am I describing when I say that? Integers. So you just have to make a little note every time you use this notation and say K is an integer. So again, make a note for yourself how we wrote this equation. 3 was the distance between them, the number we want people to keep using repetitively. That's why it's getting multiplied by something. And 1 was just chosen because it was a good starting point for them to start at, because it was something from the list. Okay? So, why don't you guys go ahead and try to write the range for the second graph with the people at your table, and then we'll check it. Okay, anybody willing to share? Yeah. And then this is kind of annoying, you guys. You do have to keep writing where K is an integer. If we're doing a bunch of this, your test isn't going to be a bunch of this because this is one part of the unit. But if you were doing a bunch of these, you can write at the top of your paper like K indicates an integer, and then I will know the whole time. But if you don't say it anywhere, or you don't say it like as an overall arching thing, and you don't say it in the problem, then we don't know. So notice what he picked. Why is there 1/2 here? Good, because that's like how much we want to jump to get to the next step or the next number that would be in the list of the range. And then he chose 1 because 1 is an adequate starting point because that is a value we do obtain in our range. Okay? Anybody else write it differently? Everybody chose 1/2 x plus 1, right? Oh yeah, K, thanks. Oh yeah, so he did 1/2 k, right? Why doesn't he have anything added on to it? Is 0, and 0 was an acceptable number in this case, so we left it. In this one, we couldn't hit 0, right? 0 was not part of the range. That's why we really had to make sure that we hit something, okay? Yes, Haley. On here, it's 1.5, and this one's open. But remember, the range is just, do we ever hit that y value? It doesn't have to be the exact y-intercept. So he's allowed to use 1 as well because we do have a bunch of points where 1 is the y value. So if I made the list, I'm not really putting, this looks like a line, but this is not the equation of the line. This is an equation to find all of the y's that are listed in the range. So if we started listing in the range, yes, 1.5 is one of them, but so is 1, so is 0.5, because even though there's an open circle there, there's a bunch of other points that have a y value of 1 with them. Does that make sense? So that's why there's so many answers here, because as long as you started on one of these things, and then you moved up or down increments of 1/2, you would hit all the numbers that we would list. So it doesn't really matter. If we were writing the equation of a line that went through that point, yours would be the only one that we could use. But given we're writing an equation of just this list, we can start anywhere in the list, and those 1/2 jumps would get us to those other places. Is that okay? Okay. Any other questions about this? So your homework is skills 7 and 8.